Hi, welcome back to engineeringtalks.com. Today we'll be discussing the topic shear force and bending moment diagrams of a cantilever beam with a uniformly distributed load. So, happy learning, and if you haven't subscribed the channel yet, please do subscribe and press the bell icon. Here I have shown a cantilever beam with a uniformly distributed load over it. In the previous video, I have clearly explained the different types of beams and the different types of loadings. So please watch that video in order to have a clear understanding of the types of beams and the types of loadings. This is a cantilever beam. A beam which is fixed at one end and free at the other end like this is known as a cantilever beam. And this is a uniformly distributed load. A uniformly distributed load is the one which is spread over a beam in such a manner that the rate of loading W is uniform along the length of the load. In this case, since this load is spread over the entire length of the beam, we can say that the rate of loading W is uniform along the length of the beam. For solving numerical problems, what we usually do is that we convert this UDL, that is uniformly distributed load, into a point load acting at the center of the load. In this case, we can say that the equivalent point load will be acting at the center of the beam. So, center of the beam means L by 2, a distance of L by 2 from both the ends. And the value of the point load will be equal to this W into the length of the load. So, length of the load here is L. So, W into L. So, this point load W into L will be acting at the center of the beam like this. So, this is a cantilever beam of length L with a uniformly distributed load over it, and the rate of loading is given by W per unit length. First of all, let's find out the values of shear force and bending moment along the length of the beam. For that, let's consider a section X at a distance of X meter from the free end of the beam. So, this is the right portion of the section. Let's consider this portion alone. So, here is the right portion of the section. Here we have a uniformly distributed load spread over a distance of X meter. And I already told you that for solving the numerical problems, we have to convert the UDL into a point load, which is acting at the center of the beam, here at the center of the section. And the value of the point load will be equal to W into the length over which the load acts. So here UDL is spread over a length of X meter. So the point load will be W into X and it acts at the center of the section. Now we can get the value of shear force acting at this section X. How? We already know that shear force is the algebraic sum of the forces acting either to the left or right portion of the section. Since we have considered the right portion of the section here, shear force will be equal to the algebraic sum of the forces acting on the right portion of the section. So here we have only one force, Wx, which is acting in the downward direction. Any force acting in the downward direction on the right portion of the section is considered as positive. Therefore, the shear force at this section is given by plus Wx. If Fx is the shear force at this section X, then Fx is equal to plus W into X. From this equation, it is clearly understood that the shear force is proportional to the distance of the section from the free end. Therefore, at B, when x equal to 0, we have f of x is equal to W into 0, which is equal to 0. And at this end A, when x equal to L, we have f of x is equal to W into L. Therefore, at this end, we have the value of shear force equal to 0, and at this end, we have the value of shear force equal to W into L, and it follows a straight line law. Next is the bending moment. So, we have considered this section. So, on the right portion of the section, we have a point load Wx acting in the downward direction. And this point load has the tendency to rotate the beam in the clockwise direction, right? So, any moment in the clockwise direction on the right portion of the section is considered as negative. Therefore, the bending moment acting at this section will be equal to the force into the perpendicular distance, that is Wx into x by 2. Since it is in the clockwise direction, the value will be negative. Therefore, minus Wx into x by 2, which will be equal to minus Wx square by 2. And from this equation, we can understand that the bending moment is proportional to the square of the distance of the section from the free end. That is, it follows a parabolic law. Now at this end, when x equal to 0, bending moment mx will be equal to minus w into 0, that is 0. And at this end A, when x equal to L, we'll have mx is equal to minus w into L square by 2. So at B we have mx equal to 0, at A we have minus WL square by 2. Now let's draw the shear force and bending moment diagrams. First let's see how we can draw the shear force diagram. For that, let's draw the baseline first. So this is the baseline. We know that at this end the value of shear force is 0 and at this end the value of shear force is plus W into L. That is, its value is positive. So the positive values will be plotted above the baseline and we usually indicate the shear force using vertical straight lines like this. Now we'll join this point and this point using a line like this, straight line like this, since it follows a straight line law. That is, shear force is proportional to the distance of this section from the free end. That is, it is a function of x. So it follows a straight line law. And the value is positive. And you can shade this region like this. So this is the shear force diagram and the value of shear force at this end is 0 and the value of shear force at this end is plus W into L. Now let's draw the bending moment diagram. For that, let's draw the baseline first. So this is the baseline. And you can mark it as well. Okay. Now we know that at this end the bending moment is 0 and at this end the bending moment is given by minus W L square by 2. It is negative. So we have to plot it below the baseline. So this is W L square by 2. Now we have to join these 2 points, right? But we cannot join it using a straight line. We have to join it using a parabola because bending moment follows a parabolic law. That is, bending moment is proportional to the square of the distance of the section from the free end. So we have to indicate that using a parabolic curve like this. And the bending moment is negative. And you can shade the region as well. And you can mark the ends A, B. Here you can mark it as A dash. So this is the shear force diagram and this is the bending moment diagram. So this is the shear force and bending moment diagrams of a cantilever beam with a uniformly distributed load acting over it. This is the shear force diagram and this is the bending moment diagram. Here we have a straight line and here we have a parabolic curve. Please do like and share the video and subscribe the channel. Thank you.